Welcome to the Future Lab. I'm your host Matthew. Today, we're exploring a groundbreaking research paper that uses large language models, or LLMs, for materials language processing, or MLP. This is a big deal because it tackles a major hurdle in materials science, extracting useful data from the massive amount of unstructured text in scientific papers. Think of all those research articles, a goldmine of information, but locked away in a format that's tough for computers to understand. This research shows how we can unlock that information using AI, making materials research much more efficient. We'll be exploring three key areas: the research's main ideas, a deep dive into the methods used, and then a discussion of how this impacts materials science and where it's all headed. And just to add a fun element, this episode's script was AI assisted. It's a great example of the very technology we're discussing. So, let's start with the core of the research, the key ideas behind this work. So, the paper, Accelerating Materials Language Processing with Large Language Models, by Choi and Lee, really gets to the heart of a big problem in materials science. Right now, extracting useful, structured data from all those research papers is incredibly time-consuming and relies heavily on manual work. It's a real bottleneck, slowing down research progress. Their solution is elegant in its simplicity: use the power of large language models, LLMs, to automate the process. The core idea is that LLMs, like GPT models, can be trained to identify key information, such as the materials used, their properties, and the relationships between them, all from the text of scientific papers. And the amazing thing is that they found LLMs can do this with surprisingly high accuracy, even when they only have a few examples to learn from. That's what's known as few-shot learning. They tested this approach on several key tasks: text classification to filter relevant papers, named entity recognition to identify specific materials and properties, and question answering to retrieve key information. The results? Significant time savings through automation, leading to much faster analysis and potentially, faster materials discovery. This is a compelling improvement, but how did they actually achieve such high accuracy? That's what we'll explore in our next section, a deep dive into their methodology. Now let's get into the nitty-gritty. How did Choi and Lee achieve such impressive results? Their approach cleverly uses the power of large language models, specifically GPT models, and they explored three main techniques. First, there's zero-shot learning. This is where the model uses its pre-trained understanding of language, its knowledge of words and how they relate, to classify text without any additional training on a specific dataset. It's like giving a really smart student a complex question and seeing if they can answer it based on their general knowledge. Next is few-shot learning. Here, they give the model a small set of examples to help it understand the task better. It's like giving that same smart student a few examples of similar problems before posing the main question. And finally, there's fine-tuning. More like giving the student an entire textbook on the subject before the exam. Fine-tuning means training the LLM further using a much larger dataset of labeled examples. But it wasn't just about these three learning techniques. A crucial part was prompt engineering. They carefully crafted the prompts, the instructions given to the model, to guide its analysis and extraction of information. Think of it like providing clear and concise instructions to a researcher in your lab. You need to be specific and avoid ambiguity for good results. This meticulous prompt engineering was key to their high accuracy in both text classification and entity recognition, even with the zero and few-shot methods. They went further, applying their LLM approach to another important task: extractive question answering. Using a material science-specific dataset, they showed the model could effectively retrieve specific, targeted information, answering questions accurately based on the information provided in the text. But here's a really innovative aspect of their work. They used the LLMs to actually help identify errors in existing, manually labeled datasets. This demonstrates a powerful potential: LLMs not just as tools for data extraction, but also for improving the quality of our training data itself. However, there's a significant aspect we need to consider. Since these methods leverage the generative abilities of LLMs, their ability to produce text, there is a risk of hallucination. That's where the model might generate information that isn't actually present in the original text. So, while these methods are effective, they require careful validation to ensure the results are reliable. This brings us to the next stage, considering the real-world applications and implications of this work. The implications of this research are truly transformative. Imagine the impact of automating the extraction of structured data from scientific papers. We're talking about the potential to automatically build comprehensive databases of materials and their properties. This would dramatically cut down the time and effort currently spent on tedious literature reviews, a huge time saver for materials scientists. And the effect would ripple outwards, speeding up materials discovery and development across the board. This isn't just about one specific area, either. The methods they describe, using LLMs for text classification, entity recognition, and question answering, can be applied across many different materials science fields. Think about accelerating research in everything from battery technology to new construction materials to advanced electronics. Specifically, this AI-driven approach can easily automate dataset creation for machine learning models. Models which predict materials' properties or even guide the synthesis of entirely new materials. That's how powerful this could be. And it's not just for machine learning experts. This opens up exciting opportunities for researchers who might not have that specialized knowledge to use these powerful tools and contribute more to materials research. It's a real democratization of access to powerful analytical tools. Ultimately, this research represents a major advance over previous deep learning methods. It addresses the limitations of those approaches, the need for massive manually labeled datasets and the development of complex models, making the technology more accessible and practical for use in many different research settings. This method is highly significant, but what about the future? What are the next steps in this exciting area of research? Let's explore that in our final section. So, to wrap things up, let's recap the key takeaways from Choi and Lee's research on using LLMs for materials language processing. Their work shows the real potential of LLMs, particularly GPT models, to dramatically improve the accuracy of tasks like text classification, named entity recognition, and question answering in materials science. They achieved this even with surprisingly small amounts of training data, a significant advantage. The clever use of prompt engineering was absolutely crucial to their success, showing just how much you can influence the model's output with careful design. And the fact that they could use these LLMs to actually find errors in existing datasets is a real game changer. It speaks to the potential of LLMs to not just extract data, but improve data quality. This research could truly streamline materials research, creating far more efficient workflows for scientists. However, we need to remember that challenges remain. The generative nature of these LLMs does introduce the risk of hallucinations, the models producing information that isn't actually there, so validation is a crucial step to ensure accuracy. Despite those caveats, this research really does open up a fascinating new frontier in AI-driven materials science. It's a clear demonstration of how LLMs are transforming how we approach and accelerate scientific research. And it highlights that the future of autonomous research is rapidly approaching, with LLMs playing a central role. This has been another episode of the Future Lab, and don't forget that this episode's script was itself AI-assisted. Thanks for listening. Join us next time as we continue to explore the rapidly advancing world of AI and its transformative impact on scientific research. Until then, stay curious.